Hello, welcome to my shop. Today I would like to present a fine adjustment device for the tilt angle of a milling table. This will be a two-part video. Here is the first one. This is what the finished piece will look like. The tilting table of my teel is locked in position with the help of two clamping screws. When trying to tap the table precisely to a certain angle using the dial gauge, there are two possibilities. The clamping screw is too tight and nothing happens, or it is too loose. At times I have used a screw jack as a makeshift adjustment tool. Now I want to find a better solution. The design is inspired by the fine adjustment of this protractor. The two parts can be fixed with the help of a clamping screw Two pins are connected with a set screw consisting of a right hand and a left hand thread. Thus, their distance and therefore the angle can be very finely adjusted. And this is what the CAD model, adapted for the machine table, looks like. You can see that the threaded rod has to be able to swivel a little bit. That's why I use round bronze bolts with cross threads. The bolts will later be pivoted. Instead of right hand and left hand threads, I use threads with different pitches, M10 by 1.5 and M10 by 1.0. Let's start with the production of the bronze threaded bolts. Firstly, the usual facing. The circumference is turned cleanly to 16.5 mm. The exact dimension is irrelevant for the time being. I repeat the whole process for the other side of the rod. I produce the cross threads on the milling machine. Finding the center with the edge finder and drilling. Drill the core hole to 8.5 mm. and tapping the M10 by 1.5 thread. And the same steps for the second bolt, but this time with M10 by 1.0. Finished. We continue with the machining of the differential threaded rod. This consists of two approximately 80 mm long threaded sections, M10 by 1.5 and M10 by 1.0. A 30 mm hex will be milled in the center. Both ends of the blank are turned flat with an undercut of approximately 80 mm diameter and a centering hole. To be honest, I was not satisfied with the result of the first attempt. Here I show the newly manufactured threaded rod made at the very end of the project. A hexagon for a 30 mm wrench size should remain in the center of the rod. I turn the rod to the outer diameter of this hexagon. Then I turn both halves of the rod to 10 mm for the M10 threads, up to the length of the hexagon. Generously dimensioned undercuts will allow relaxed thread cutting in the next step. No thread will be required in this area later, so that will work. Checking the thread pitch. I use a high-speed steel cutter ground on the tool grinder. I take things slowly and only add 0.025 mm, about 1/1000 on radius per cut. It is very convenient that the 1.5 mm pitch of my lead screw corresponds to the thread pitch. This allows the half nut to be opened and closed as required. After numerous passes, deburring and cleaning, the bronze nut fits perfectly. Free moving, but almost free of play. I repeat the procedure on the second side, this time for M10 by 1.0. However, I must not open the half nut here. Thanks to the wide undercut, this is no problem. Patience is rewarded with a perfect result. I produce the 13mm hexagon on the milling machine. The video shows this using the differential thread rod produced first. To be honest, I was too lazy to film it again. A quick test shows that the differential thread works. The main item of the fine adjustment is now finished and needs to be mated to the table somehow. So let's take a quick look at the design. One of the threaded bolts is to be slewably connected to the tilting tabletop. Here a relatively simple trunnion stud is sufficient into which the threaded bolt is inserted so that it can rotate. The trunnion stud is bolted to the arched clamping section. The design of the trunnion stud, which is connected to the fixed table base, is slightly more complex. The stud is mounted through the semicircular slot of the tabletop and bolted to the support of the table base. Here too the bronze threaded bolt is inserted into a suitable hole. The table is clamped with the clamping device pushed over the stud. The next step is the production of the trunnion stud. The blank is prepared as usual. Facing, center drilling, turning the OD. The workpiece is step drilled. The hole that accepts the bronze bolt is bored out. A grinding vise serves as an improvised longitudinal stop. I start with a cheap Chinese carbide boring bar and switch to a proper boring bar with an indexable insert as soon as the diameter is large enough. The bronze bolt fits. Now the hole is enlarged about 20 mm deep for the thread for the clamping device. Again I use the vise as a stop. The fact that I use a gauge block here is not due to the required precision, but it is simply more practical than a caliper gauge in this case. And we continue boring out. Excuse my hairstyle, I went straight out of bed into the workshop. I still have some boring bars from a collection of tools which hold the corresponding carbide inserts with the help of a dovetail. I ground a suitable thread cutting insert on my tool grinder. As I don't like to cut the thread blind against the shoulder, I mount the thread cutter upside down and run the machine in reverse. This means that the thread is cut from left to right, nevertheless it is still a right hand thread. First I make a relief groove from which the cut will later be started. As the exact dimensions of the thread are not important, I decide on a pitch of 1.5 mm, corresponding to the lead screw pitch of my MCO lathe. This means I can open and close the half nut as required. This makes the work a lot easier. The tip of the cutter is positioned in the relief groove using the dial gauge. Then the half nut is closed, turning the spindle slightly if necessary. The cut is made after feed is added on the cross slide. Here I break the edge. The part that is inserted through the half-round slot of the top table is turned down a little. The measurement is not critical. In retrospect, it would have been better to carry out this step before boring out and with tailstock support. After parting off, facing and deburring, the lathe work is finished on this part. Now comes a piece of sophisticated German engineering. You could also call it over-engineering. The base of the trunnion stud must be curved so that it fits through the semicircular slot of the tabletop. Of course, it would be perfectly adequate to mill two flat surfaces, but I want to produce matching radii here. To do this, I first determine the radius of the curve. I insert a bolt into the thread of the clamping screw and measure the distance between this bolt and the existing bolt of the tilting table. I also determine the diameters of the bolts. These values result in a radius of 165.8 mm. I do not have a rotary table at my disposal. The arched surfaces could be machined with a faceplate on the lathe, but the faceplate turns out to be too small. So I will bore out the rounded surfaces with a Wohlhauper facing and boring head. To do this, I clamp the stud in the vise of the milling machine. Since the 3 microns are not relevant in this case, eyeballing with a centering drill as a visual reference is sufficient. But it is supposed to be over-engineered, so I center with the DTI. First of all, an M12 thread has to be tapped. Thus I pre-drill with a 10.2 mm drill and tap the thread. I turned a bush from a piece of aluminium that fits exactly into the arched slot. This will later serve as a reference. The table is adjusted to the previously determined radius of 165.8 mm in X. I machine the inner radius with the boring bar, which I insert into the UPA 5 and touch off. I set the depth stop on the quill. The first pass is made with a minimal infeed of less than 0.1 mm. Here the reference aluminium bushing is just barely scratched, so this is the final cut. I am more than satisfied with the surface finish. When boring the outer radius, the extension arm collides with the Z column of the machine. So the vise has to be moved further away and the workpiece recentered. You can practice this often enough. As there is also very little clearance at the top, I set a temporary stop. A dial gauge is normally clamped here. Because of the strong imbalance, I have to reduce the speed to about 100 RPM. A counterweight allows the speed to be increased to 270 RPM. The freshly ground high-speed steel initially performs quite well. As the trunnion stud should fit into the groove with as little play as possible, I measure the width of the slot with gauge blocks and a gauge pin. At some point I noticed chatter marks and the cutter no longer seems to cut cleanly. I had probably hit the head of the Allen screw that secures the aluminium bushing. Regrinding does little good. That's why I use a tool reground from a broken solid carbide end mill. This cutter produces an excellent surface. I determine the thickness of the tenon with a micrometer screw and the gauge pin. I am satisfied with 0.03 mm undersize. Unfortunately, the shoulder didn't come out clean, as I first had to regrind the cutter and then replace it. But why not making use of the facing mode of the Wohlhauper? As I have to face from the outside inwards against the existing shoulder, I set a stop on the Wohlhauper. The head is fed via the knurled ring. A lever holds this ring in place via a spring-loaded bolt. When the stop is reached, the force exerted on the ring increases and unlocks the bolt. As a result, the feed ring rotates freely and the feed stops. The stud fits into the slot with virtually no play. Perfect. Was it worth the effort? Economically speaking, certainly not, but it was fun and that's why it was worth it. This concludes part 1 of this video. It continues in part 2, in which the fine adjustment device will be completed. Thanks for watching and hopefully see you in part 2.